Let's look at the mean value theorem for integrals. If f is continuous on a closed interval ab, then there's at least one point x star in ab such that this. Okay. Now, what does this mean? The area under the curve, right? There's at least one point x star in this interval where the area under the curve is equal to f evaluated at that x star times b minus a. All right, so what does that mean geometrically? Let's look at it geometrically, okay? Here is f. Now, if we're looking at this side of the equation, the integral of f from a to b, what does that mean? That means the area under the curve, or between the curve and the x-axis, from a to b right here. Let me extend this a little further so I can reach b. That was f. From a to b, okay? So this is what we're looking at on the left side. The area under the curve is an interpretation of that, okay? Now, what does this right side mean right here? F of x star is equal to b minus a. What that means is there's a point, x star, somewhere between a and b, and maybe that point's about right here. I could call that x star, okay? And if I go up to my curve right here, that's my function f evaluated at x star right there, okay? And then what is this? F of x star times b minus a. What that is think about from a to b, okay? B minus a is the length of that interval. What we're going to think of geometrically right here is that we have a rectangle here, okay? What this is a rectangle with width b minus a and height f at x star. And what they're saying here is that the area under the curve, the part shaded in black, is equal to the area of this rectangle with a height of f of x star and a width of b minus a, okay? So the area of, maybe I'll draw these the other way. The area of this rectangle is the same as the area under the curve. So there exists some point x star in the interval from a to b to where the rectangle with height f of x star and width b minus a is the same as the area under that curve, okay? So what we're going to do in some of these problems is we're going to find that value, f of x star. All right, let's see. Let me erase this and we'll get to our example on the notes. Okay, so on the notes we have find all values of x star that satisfy the conclusion of the mean value theorem for integrals. And we have f of x is equal to the square root of x, and we have the integral from 0 to 3, okay? Now the mean value theorem says if f is continuous on a closed interval from a to b, is this function continuous from 0 to 3? Yeah, think about what it looks like, okay? Doesn't our function look like that? And if we're looking from 0 to 3 right here, it's continuous, right? So if f is continuous on the closed interval from a to b, then there's at least one point x star in ab such that, all right, so we want to find x star that satisfies the conclusion of the mean value theorem. What is the mean value theorem, what we just had? The integral from a to b of f of x dx is equal to f at x star times b minus a, right? Now this is a, this is b, remember my interval. So if I fill in now, I have the integral from a to b, so the integral from 0 to 3 of f of x, which is square root of x dx, is equal to f at x star. So what does this mean? This means evaluate f at x star. So you're going to have the square root of x star instead of x times b minus a. 3 minus 0, and we want to find that value of x star, okay? So let's see how we do this. Well, let's do a rewrite. Let's call that the integral from 0 to 3 of x to the 1/2 dx is equal to the square root of x star times 3, right? Let's take this antiderivative. In other words, let's evaluate the integral on this side. So I'll be x to the 3/2 times 2/3 from 0 to 3 is equal to, I can commute these around and call that 3 times the square root of x star there. So now let's evaluate this antiderivative at 3 and subtract it, evaluate it at 0. So that's 2/3 times 3 to the 3/2 minus 2/3 times 0 to the 3/2 is equal to 3 times the square root of x star. So what do we have here? We have 2/3 times 3 to the 3/2. This part just zeroes out, right? Because the square root of 0, 0, 0 cubed is 0, times that is 0, is equal to 3 square roots of x star, right? Now, we're still solving for x star, so we can either divide both sides by 3 or we can multiply by the reciprocal, right? So I'm going to multiply by reciprocal. 1/3 times 2/3, 3 to the 3/2 is equal to the square root of x star here. All right, so what does this give me? This gives me 2/9 times 3 to the 3/2 is equal to the square root of x star. Now let's look at putting this 3/2 over 1. Now let's think about this for a second. Instead of putting 9 there, 3 times 3 is 9, what I could do is I could put just 3 times 3 here, and it might make the simplification process easier here. Let's see. The understood exponent here is 1. So what happens when I divide these out? All of this one divides out with 1 from here, right? So instead of 3 to the 3/2, it'll be 3 to the 3/2 minus 1, right? Or that'll be 3 to the what? 1/2. So I have 2 over 3 here times 3 to the 1/2 over 1, right? Is equal to the square root of x star. Now this has an understood 1 on it as well as the exponent. So I can divide out all of those 3's there with 1/2 of them here, so that's 3 to the 1/2 there. So what am I left with? 2 times 1, or 2, over 3 to the 1/2 times 1, or 3 to the 1/2, is equal to the square root of x star. Now how do I get to x star? I square both sides, right? So 2 over 3 to the 1/2 squared is equal to the square root of x star squared. All right, so what happens whenever I square 2? I get 4. What happens whenever I square 3 to the 1/2? I get 2 times that 1/2, or I get 3 to the 1st, right? Is equal to x star. Now let me ask you this. Is 4/3 in the interval I'm looking for? Because this number right here needs to be in that interval. Yes. Is it between 0 and 3? So what were they saying? They were saying what? Find all values of x star that satisfy the conclusion. Here's my value of x star that satisfies that. Now let's see if it kind of makes sense in my head, okay? What do we have? We had the square root of x. I'm just kind of checking to see if I'm somewhere in the right ballpark here, okay? Square root of x looks like this, right? I'm looking between 0 and 3 right here, right? Now let's see, where is 4/3? That's what? 1 1/3? So that's 3, then this is about 1, that's about 2. So 1 1/3 maybe is about right here. And that's that x star value, right? Now, if I draw a rectangle from here to here, that looks like it'd have about the same area under that rectangle as I have as area under my curve. So I'm probably in the right ballpark. All right, so let's see what's next. What's next is the Fundamental Theorem of Calculus Part 2. The Fundamental Theorem of Calculus Part 2. FTC Part 2. What does that read? According to your notes, that reads, if lowercase f is continuous on an interval, then lowercase f has an antiderivative on that interval. In particular, if a is any point on the interval, then the function f defined by capital F of x is equal to the integral from a to x of f of t dt is an antiderivative of lowercase f, that is capital F prime of x is equal to lowercase f of x for each x in the interval, or an alternate notation. Okay, don't worry, I'm going to explain this. The derivative with respect to x of the integral from a to x of f of t dt, they're saying is f evaluated at x. All right, let's look at this alternate notation here, okay? It's saying, suppose I want to integrate f of t, and I have a lower limit of integration that's some number, some constant. Upper limit of integration is x. Okay, I want to integrate that, then I want to take the derivative with respect to that upper limit of integration x. Then what do? All I have to do is I have to take this integrand here, this function here, and evaluate it at that upper limit of integration. Okay? Again, constant lower limit, x my upper limit. I'm taking the integral, then I'm taking a derivative. What do? I just take this function, evaluate my upper limit of integration. They're trying to show you that taking a derivative and integrating are inverse operations. They undo each other, like addition and subtraction. All right, so let's look at our example. Our example says this. It says, find d over dx. Find d over dx of this thing, the integral from 1 to x of t squared dt. Okay, part A, by applying part 2 of the Fundamental Theorem of Calculus. Okay, so if I apply part 2 of the Fundamental Theorem of Calculus, do I have a constant as my lower limit of integration? Yes. Do I have a variable as my upper limit of integration? Yes. Is that variable the same as what I'm trying to take the derivative with respect to? Yes. So what does this tell me I can do then? Just evaluate this function at the upper limit of integration. So all I'm going to do is I'm going to evaluate t squared at x. So wouldn't that just be x squared? Yeah, we're showing if you take the derivative and integrate, your inverse operations, they undo each other. All right, let's look at part B here. Part B says, what? Find this thing by what? Performing integration, then differentiating. So I want to find d over dx of the integral from 1 to x of t squared dt, taking the integral here and then taking the derivative. So let's see, we get d over dx of, what's the antiderivative of t squared? T cubed over 3. And we need to run it from what? 1 to x? So that's going to be the derivative with respect to x of, evaluate this antiderivative at my upper limit, x cubed over 3, subtract from it This antiderivative evaluated at 1. 1 cubed over 3. Now let's take the derivative. What's the derivative of this part? 3 times the front will be what? 3 times 1/3, or what? 1x squared. Minus, what's the derivative of this part? 0, so that gives me what? X squared? Is that the same thing I got before? Sure is. So as you can see, it's a lot quicker using part 2 of the fundamental theorem of calculus. Now, what if you had an example that said, do this? Let's say we had x to, say, 1, or I'll tell you what, let's just take -5, okay? X to -5 of t to the 6 dt, and I want to take the derivative with respect to x of that, okay? And I want to use the fundamental theorem of calculus part 2. The fundamental theorem of calculus part 2 says make sure you have a lower limit that is a constant, and the upper limit is that variable that matches that variable. Well, I have just the opposite, right? But how could I switch these limits of integration? If I did what? If I called this a negative integral for -5 to x of t to the 6 dt, right? Now remember, if you're taking a derivative of some constant times your function, what could you do with that constant? You could factor it out to the front and call that negative d over dx of the integral from -5 to x of t to the 6 dt, right? So that gives you a negative. Now lower limit's a constant, upper limit's a variable that matches that variable. So what do I do with this? I'll call it x to the 6. There we go. Good luck with the homework, folks.